Okay, our final talk of this morning is from Professor Ima at the UC Berkeley ECS department. Professor Ima is a renowned and a very influential researcher in computer vision and machine learning, where his work on computer vision has won a couple of awards, such as Morris Award at the CV, and other awards at ECCV and ACCV. Professor Ima is a fellow of several organizations, such as IEEE Fellow, Fellow of ACM, and Fellow of SAM. Professor Ima is a highly cited researcher in our area, where he has over 50,000 citations. And interestingly, he is also an active blogger on Chinese social media, such as Weibo, where he has over 70,000 followers. Professor Ima is author of three books: An Invitation to 3D Vision, a Generalized Principal Component Analysis, and recently has a new book, highly anticipated new book about to come, which is called High Dimensional Data Analysis with Low Dimensional Models. The reason that I know E is because he is my PhD advisor's advisor. And about a decade ago, I decided to do my PhD. It's because it's very influential work on high dimensional data analysis with low dimensional structures, such as robust face recognition, robust PCA, and dictionary learning, which is really inspiring and exciting at that time. Professor Ima's current research focuses on 3D vision and moreover, deep networks with low dimensional structures, which well aligned with the theme of this workshop. And recently we are also fostering some collaborations along this line of work. Today, Professor Ima will give a talk on his recent work, deep learning from first principles. So let's welcome E.
To figure it out a little bit. So this is sort of a quest. I remember the first time I came to Berkeley, I had a coffee with Emmanuel Candace at Stanford. So that's where the story started. We were chatting about all these things, what's kind of happening. But we actually had a gut feeling there is that there should be very fundamental connection, right? A lot of things that the neural networks, the structures, the practice, there's a lot of similarity to, although mostly from an empirical point of view, but there's a lot of similarity from the kind of the methodology or method or structures we're dealing with low dimensional structures. But of course, nothing is really quite concrete. We don't really know. I mean, there's a lot of mysteries about the neural networks. So in the next 2 or 3 years, I'm very much sort of find myself chasing practitioner's tail, right? So that's, I hope most of the probably theory people, oriented people has that feeling that every once in a while, practitioner tell us something works, something don't work. We try to write a paper to explain why. Try to sort of very much, basically flattering them. What you're doing is right, from a theoretical point of view. But yet there's a tremendous gap, right? Because practitioners don't care anything about what the theoretician says, right? It's always just chasing hundreds, thousands of papers, just try to explain whatever little bit everybody does in practice, right? So from a theoretical point of view, I even wrote quite a few papers around that about several things. Feel like we're touching a big elephant, basically, right? This is involve many components, different things. So about a year ago, something strikes me, right? So see, we got so many nets, right? This nets, that nets, just like even wavelets, we have so many nets, right? And also that if you realize, do a little bit, I just said this situation cannot continue, right? This huge gap between theory and the practice. Yet, we somehow theoreticians get lost. We're just get dragged by all these little things, right? Trying to explain, what works at initialization, what happens with gradient descent, what happens, things we understood very well a long time ago. But somehow we're just reinventing a lot of things to explain what the practitioner does. And another phenomenon, notice that in nature, right, physics systems and also society, it's a very complicated system. This is hundreds, thousands of instances. Every instance is different, but they're all governed by very simple principles. Right? Biology is for survival, right? Physics is for minimal time, energy, and so on. right? And also society is for utility, right? Everybody trying to make money out of it. Also about survival, right? So this is other things that, after a while I start realizing that maybe can we go back to, we cannot do this. So can we go back to the, drawing board, derive everything from scratch? Is that possible or impossible for deep learning? Right? That's actually sort of, today's talk has something to do with that. I think we are making a first step towards that direction. Right. Because of this, I completely changed my methodology about a year and a half ago. Right. I just stopped myself to try to explain everything that a practitioner does, tells me what works. Right. So you can ask a few very, very hard questions. What are our assumptions? What are we trying to do? What's our goals? Right. About learning in general. Right. If we can understand this a little bit better, if along the way deep networks or not come along, so be it. Right. But we're back to the original, what do we want with deep learning? And so that actually, brought me back to some work I did with actually John Wright about 15 years ago. Turns out actually we started doing this even before we were worrying about we're doing deep networks or deep learning. We'll get to that in a second. So today, sort of reconnected to the very simple principle towards data compression, right? And we will get to that in a second. So this is sort of the line I will get to. So we start with a very basic question. So what is learning, right? What do we want to do with data, right? Before all the fancy things, back to the scratch, right? Well, there's, age-old questions in pattern recognition. We have data. So there's three things we do. We want to interpolate data, find the nearest neighbors, do linear interpolation, right? And in fact, all the fancy things you see, including GANs or image imprinting, right? It's really doing this, just the different names, right? We have I sort of joke around, right? Mathematics is the art giving the same name to different things. That's what we should do, theoretician, right? Artificial intelligence is sort of it's the art of giving different names to the same thing. There's a little bit of truth to that. Then what's the next? After you're able to figure out the near neighbors, you extrapolate. You have a new sample comes in, you find which one is closer to which class. It's classification, right? And another thing is that, of course, we're not happy with the raw data. We don't want to record all the raw data. We want to find something law behind it, right? Some mechanism. So we find a representation. If all the points lie on a line, we just have to record the parameter of the line. So find some discriminative or compact representation. That's very much it, right? Everything we do with data, that's the three things, falls into one of those categories. Now, but deep learning comes along, says that we can actually just lump everything into this black box, right? Try to convince everybody, right? Just fit it from your data, go fit the labels. Give me the labels, I'll just fit it. And of course, it works and actually capture a lot of people's imagination. There's a lot of actually usefulness to this. Sometimes you actually don't care the tools. So, but there actually, of course, there's actually a big elephant in the room is that there's a lot of problems, right? Of course, you can, minimize the cross entropy, and then you can actually turns out that there's a lot of, sort of mysteries, right? So people realize if the network is big enough, it's very flexible. If you make it, and it actually can fit any data, even arbitrary labels, arbitrary input, right? That's how powerful it is. Right? Also, that because it's a black box, you don't really know what you learned, right? It's what all those parameters doing. So far from I'm in computer vision, so far the best people can do is just visualize one neuron at a time, right? One node at a time, using deconvolution and so on. Right? It's pathetic, right? We don't really understand what's going on. And also the practice, the methodology is very task data dependent, right? Once I change the data, then all the task, I have to return neural networks. Of course, there's a lot of talks about the transfer learning, well, I haven't seen anything impress me, right? So it's a concept, right? You can do that, but there's really no principle, no guarantees how things really succeed. Now, then you ask the question, remember our original, right? Goals about the pattern recognition or data analysis is that interpolation, extrapolation, or interpreting the data. Has this process helped us understand any of those? I would like to argue not quite, right? So of course, there's an attempt to try to explain what happens with neural networks, right? There's one of the framework is that information bottleneck. There's a lot of information theoretical tools, concepts are introduced to try to explain what's going on in this process, right? In particular, says that maybe we're trying to minimize this so-called information bottleneck quantity, that the mutual information between the feature you learn and the model and the label, and also subtract the mutual information of the data and the label. Why you want to do this? Because they say, well, maybe this is a process to select out the most informative features and match the label the best and throw away the rest, right? I mean, there has a lot of tension and follow-ups on this, but first of all, in this talk, we're trying to argue actually this may not be the right objective, right? Because they try to just find the minimal informative features. In some that doesn't really help enough about understand the data, because the data is what we care about, especially when you're doing extrapolation or interpolation. And also, it's task label dependent, right? You do a lot of analysis with the CPU bottle information, but it requires Y, and then you actually had a lot of trouble while trying to generalize your understanding. Actually, there's a lot of big elephant in the room. We're dealing with a lot of elephants here, but people don't talk about them, right? And this is exactly the elephant that John Wright and I encountered about 15 years ago when we were trying to apply the classification clustering to computer vision problems. I'll tell you what it is, right? You probably get the feeling this that you read machine learning papers, they all start with wonderful, information theoretic formulation, you maximize, right? Including GANs, right? Just the role you just talked about, right? We're minimizing entropy. We're minimizing the difference between mutual information. We're minimizing KL divergence, and also maximal likelihood or maximal posterior, right? Those are the things we taught in statistics. Beautiful theory framework. But the problem is that those framework has a tremendous difficulty connected to practice. Why? Almost none of those quantities I mentioned above are computation friendly. Okay, why? Any of the quantity, if you want to estimate correctly, right, or accurately, there's a curse of dimension. The sample size goes exponentially. By the way, there's even more serious problem. None of this quantity are even well defined when the data is low dimensional, which is the theme of this workshop. When you're dealing with high dimensional data like images, the structure is always low dimensional, right? That's why after the GAN, although it's proposed it's minimized some KL divergence, turns out the two divergence, the distance do not even exist. Then what the heck are we minimizing? Of course, everybody do, oh, let's relax, or let's approximate, or let's do Earth moving. Hence, WGANs, all the GANs get introduced, right? But after all this approximation, gross assumption, things should be independent, just to make things computable, right? How can you provide any guarantees? Just ask yourself that question, right? This is exactly what happened about 15 years ago, right? We're dealing with Renee, John Wright, we're dealing with, trying to cluster data in high dimension that has low dimensional structures. Actually, we found that, of course, there's nothing wrong with the theory, with the concept of information theory, but the question how to make them computable, right? One, the bridge we actually found is that actually compression, right? In fact, even the principle for the generic cases, they're also doing compression. Now, if you have low dimensional data, it will make more sense to talk about the compression. That's why I'll give the first part of the talk, I'll give a little bit of overview of what we did, what we went through very painstakingly, right? Realizing all those problems about 15 years ago, right? So now, first let's do interpolation. We have a bunch of data. We try to figure out how many clusters, how many subspaces there are, or how many, how many groups there are, right? Very simple. Neighbors should stay together. That's it. Right. Now, what the statistical tells you to do, well, let's just write a model this as a mixture of distribution, right? Then we try to estimate the mixing proportion pi, also the parameter of each cluster, right? Wonderful framework. Nothing wrong with it, right? So the algorithm people develop expectation maximization, right, to maximize this. Actually, Hinton was working on this back in the 90s. If you trace his papers, he's solving this problem for system ID, right? But actually, it turns out that they didn't go anywhere, right? In computer vision, nobody used this algorithm, right, in clustering. People use k-mean or other things instead. Why? Because the same problem, right? Let alone this is a very difficult optimization problem, but also the P. What is the P? You only have samples, right? Then you decide what class you choose. Even you are able to do that, right? By the way, you're doing a maximal likelihood estimation and so on. Actually, this quantity does not even exist if your data has become degenerate. Right? All kinds of problems. Right? Of course, people do regularization, approximation. Again, just go ahead, right? So you do that, but you don't really get any algorithmically or. So what do we really figure out? Why do we want to do cluster? We ask this question, right? Why do we want to fit the model at all in the first places? Or in fact, it turns out that even the maximum likelihood estimate is trying to actually minimize the coding length, right? Expected coding length. There's an information theoretical interpretation of it. So we realize that then why don't we just straightforwardly just do this, right? We just cluster to compress. Right? So this is a very, very basic idea. We only partition the data if it helps you save bits. Right. So meaning that if I put the two, let's say this image shows, right? If I put all the data in a big bag, I need a very big bag, right? There's a lot of empty space in between. But if I can split it, I only use a very small bags, right? 2 small bags. I mean, I save a lot of spaces. That's exactly the idea behind everything, right? We measure the quantity that how much the data, volumes or dimensions. Right. Turns out that then the question is, what is that volume? If I give you a whole bunch of data points, how do you measure that? Right. Turns out there's something, especially when your data is low dimensional, like subspace and so on. Since it turns out there's something very, very interesting. In the case of Gaussian or subspace, there is actually explicit formula. Although rate distortion is very hard to compute, this quantity, right, gave me a precision, epsilon, how many bits, binary bits you need to encode the data subject to that precision. It's called the rate distortion information theory. It's incredibly hard to compute, but turns out we're locked out in the case of low dimensional structures. Right? There's explicit formula. This tells you exactly, give you a very tight estimate of how many binary bits in order to save the data as a big matrix. Right? Try to remember the form of it. Right? It's kind of covariance matrix plus identity and log determinant of it. So once you basically now you have some measure of volume. Now you can do all the things. Turns out, right? Why do you split the data? Because after splitting, I measure the length, the coding length of each and sum them up. I say, then you split. Turns out this measure even encourages you to split data like this, even though you have a low dimensional structure immersed in some other high dimensional data. As long as the density is high, it will encourage the splitting. All right. Another question is that, well, we have the measure. Another question, how do we find the cluster, right? Turns out, well, there's all kinds of algorithms you can do. Of course, this problem is component humongous, right? Because then you have to check, verify every possible partition of your data, right? See which one give you the lower coding length. Well, actually turns out that the measure is very tight, surprisingly tight. And you can actually start from bottom. You only merge data if they help you save bits. So this comes up with the simplest, like linkage-like merging algorithm. But use this new metric, a volume or coding length, right? It actually worked wonderfully. I mean, this is work with John Wright and my students, right, about a year ago. It actually has tendency to find a global optimal. Extremely, despite all this greedy algorithm, right? The measure and so on is tremendously non-convex. But it actually is tremendously robust to outliers. Today, even till today, it's a mystery. Not only that, once you change the quantization error, there's a beautiful phase transition, right? That the clustering will from every point on its own and then start to form like ice cubes or hot air and so on. Right? Again, none of this is understood theoretically, but this is the nature of this object function. At the time, we didn't quite care about theory, but we just care about remember, our starting point is trying to get the clustering to work. Actually, this one works. We know that. So before the deep learning era, this is actually the state of art for segmentation on natural images, right? It has no heuristics, just this single objective compression alone give you the state of art. But of course, after deep learning, everybody doing supervised segmentation, right? Semantic, but they're actually only limited to 20, 30 categories. Here is not. It's just an image. You needed no training. It's just a statistic of your data. I give you segments. Maybe at some point we should get back to that. Of course, nowadays, this is all the things is under different names, right? Self-supervised learning, unsupervised learning, or other things, right? But it's clustering. Now, the next step. Once we understood, we know how to put similar data together. What's the next things? Well, there's new data comes in. We want to decide which one it belongs to, which cluster, which low-dimensional structure, right? It belongs to. Very simple question, right? It's a little bit of extrapolation, right? We extrapolate what we have learned from the data we have seen so far. Again, statistics will tell you, right? This classical statistics will tell you, well, let's do this, maximize likelihood, right? Or if you know some priors about the structure, do some map, right? Bayesian, right? So you try to optimize this kind of quantity. Again, you hit a brick wall very quickly. Why? What is a P, right? You only have finite samples. And also, suddenly you realize the data distributed on low dimension, not like a blob like I saw here, right? In high dimensional, those are highly, highly degenerate pathological distributions. And those maximum likelihood does not even exist. It blows up to infinity, or they're not defined off the support. What do? You have no samples. Again, of course, you do approximation. Let's relax. Let's add other, things, add noise. As suggested, people try to understand information bottleneck, the artificial inject network, just to make the formulation well defined, right? No, you don't do that, right? Nature is very clean, right? That's why probably in real world we do classification. We nobody does this, right? Everybody do SVM. Everybody do networks. I think for theoretician, we have some really soul-searching questions to ask ourselves. Why we're trying to push to practitioner things does not seem to, at least we haven't even figured out. Maybe this works, but we haven't figured out a way to make it computational friendly. Okay. That's probably the biggest elephant in the room. So then actually, again, this is actually John Wright. We actually did this, right? So with my student. So they said, then can we actually apply the compression principle, right? So the reason we assign a new data point to a new old cluster is because maybe that cluster can best explain that data, use a minimal effort, right? So basically, if I put the red dot to the green ones, because I only have to enlarge or do not even have to enlarge the bag, size of the bag at all, right? So whichever cluster can do this with the less number of bits wins. Very simple, right? So then you just find out which substructure can explain it. We call it minimal incremental coordinates. Right? It's really sort of the law of parsimony, right? The simple explanation wins. Always do that. Turns out, well, you say, well, this sounds a little bit heuristic, right? No, it's actually not. It's very, very fundamental, turns out, right? But yet, when you actually allow the sample size goes to infinity, and this actually turns to exactly converge to conceptually correct thing, that idealistic, as if you have the distribution. It actually regularizes the distribution. If the covariance matrix is degenerate, it'll regularize automatically for you with the precision you asked for. Not only that, it actually even add proper, what we call the geometric regularization. This simple idea, right? Implicit is doing all this for you for free, right? What this term, this is what we call effective dimension, actually shows up later. Right? We didn't realize how important this quantity is. Right? What does this is that when even you apply map, that's what the classical classification will do. What if the two clusters share the same map, right? The value is the same. Then how do you decide the arbitration? Turns out this term will says, okay, in that case, assign the points to the cluster with larger dimension. So basically, even helps you to sort of you err on the safe side. Right? Has a very, very wonderful interpretation. Now, actually, also this classifier has very, very different behaviors than what we see before, right? K-nearest neighbor. So if you have data, say in high dimension, even in 2 dimension, we can only draw those, right? The K-nearest neighbor will give you a classifier like this, right? And SVM with some kernel will give you something like this. Right? But you can see that this kind of classifier has a very good tendency, the compression, to extrapolate very, very well. Even in the part it haven't seen the data at all. Extrapolate based on the low dimensional structure it has seen in the data. That's it. By the way, the whole process is complete. There's no model, right? There's only a low dimensionality in the backend, right? Backend. But it's only using data to explain data. I give you this wonderful segmentation. It's both good and bad. Good is that it's very, very basic, back to the origin, just using the data, right? And also gives such a nice geometrically statistically meaningful separation, classification boundary. Bad thing is it's non-parametric. Every time you do this, you have to use data to explain data, right? So hence this leads to the question. So that's why we stop there. We actually show this, actually this works very, very well, but maybe not practical. Explain the data, but not. So maybe we want to go beyond a little bit, right? Interpret the data a little bit, right? Instead of using the raw data. That brings us to the modern age, right? Can we learn a mapping? Right, everybody talk about feature, right? Then we talk about features. What really we want from features, right? To be very, very clear, right? Don't put the beat in the bushes, right? Just tell me exactly what you want. So then we have data, let's say, points. Then we wanted to do, so when we learn a mapping, it must bring some good to me, right? Otherwise, why do I do that, right? So you have first to sort out what are the things you want from such a mapping, right? For example, if data is nonlinear, maybe we want to make it linear. We'll get to that, why it's important. And also, if the data is barely separable, maybe I want to spread them, right? Make the margin large, so that for future, when I do interpolation, I have a less, it's more generalizable. The classifier is better, tolerant noise and so on. Make it more discriminated. In fact, I didn't ask those, right? This is very much the objective of pattern recognition from the day one. And also from a non-parametric, not just from the raw data, can I just make it slightly more parametric, right? But here, the parametric model I'm talking about is more compact, not the the GPT-3 type, right? We'll get to that in a second. Now, after you say, okay, this is what I really want, then you are even qualified to ask, then why are deep networks, right? What deep network play a role in this, right? Deep network does not come first. Those questions come first. Well, of course, let's just borrow. I mean, remember we go back to talk about the deep networks, and there's a lot of problems. One particular problem with this is that it actually does not help you to learn the intrinsic structure of the data. Right? There's a very recent paper from Donohoe's group to realize, right? If you train neural network, actually turns out that just like the information bottleneck was suggested, right? It will only extract one-dimensional feature. Probably the most discriminative one, nobody knows, but maybe just the one that does the job, right? Does not help reveal what are the intrinsic rich structures in the data. Right? Hence, what we actually laid out is that, why can't we just, forget about deep network for a while? Let's just figure out what we want, right? So, well, from pattern recognition, the days of Fisher, right? We say, well, between class, we want the data to be very incoherent, very different, Or within class, they should be highly coherent or compressible. They should together, right? The volume should be small, right? And also, we don't want to have this neural collapsing. We want to learn as much as we want from the data. We want to have a very rich representation for each cluster, as long as those representations are discriminated from other classes, right? We want to understand all of those, right? Good, it's great laundry list, right? It's like a dream. And the question is, can you achieve this? Is there any conflict? Or is there a very simple principal measure for all such properties together? Actually, the answer is yes. Right. So let's get back to the compression, right? How do we measure? Now, instead of measuring raw data, because I'm trying to learn a mapping, right, feature, there must be something good about my mapping, right? Otherwise, I'm wasting my energy to learn such an F, right? I have to be very clear what F gives to me. Now, because I go all this trouble to go get F, so the Z must be better in some way, right? Now, how better? Characteristics, no. We know what it is, right? Very raw measure, bits, right? How many bits you can save the feature on the computer, right? Altogether, is given by the rate. Here I take an average, right? How many samples is that called the rate rather than the total collisions? So the average bits per sample, how you save it. Also, since it's classification or clustering, I can partition the data in between, right? But in multiple classes. Then if I do that, then there's a different measure of volume, right? Just in the clustering. I put them together or separate them. So once I split them, if I do it correctly, this volume or the average rate should be much, much smaller, right? If the data has such structure, if I did the partition correctly. Those are the two assumptions. Here is the form. Only difference here is pi. Pi is just selecting which columns or which points belongs to which group. Very, very simple. It's exactly the same formula applied to different clusters and sum them up, average. Now suddenly you have this two quantity. One is measure the whole bag, right? Another one is measure all the parts. Obviously, right? You wanted to make the difference large as possible, right? So that the feature and also the partition all make sense, right? So if you look at this first term, it says I want all my feature. If you give me this space, I want to fill them, right? Make them very distinctive. But the feature belongs to the same groups, should all stay as close as possible. It's very, very simple, right? In Chinese, 同性相吸，异性相斥. That's it, right? 5,000 years ago, we had the philosophy. This is it, right? The same thing contract, difference in contrast, right? Not under very, very different names, compress, expand. I mean, there's a lot of elements. Just, if we keep doing this renaming business, just get a dictionary, right? But what's the idea? Very, very simple, right? Think about it. You have data. Let's say I use this example of 2 lines, right? So the green ball is all you need to encode them, subject to some precision. Of course, in terms of green ball, the 2 lines are very simple, right? In terms of representation, they're equally. Left and right are the same, right? My data lies on 2 subspace, they're separable, right? But I prefer the left one, right? Representation-wise. Why? Because they're more discriminative, right? If there's noise, those 2 are barely separable, but I want them make them discriminative. That's it. Very, very simple idea, right? Everything goes back to the first principles. So hence, this looks completed quantity is doing something very basic, very fundamental. It just maximizes the number of blue balls in the space between your structure, your data, the whole and the parts. That's it. Whichever configuration maximizes that quantity, maximizes the number of balls, wins. Right? So therefore, you got this the maximum coding rate we proposed earlier this year. Right? And you will just maximize this too. But there's just one thing to notice, right? Because you are comparing space, left and right, right? Imagine, what if you're counting the blue balls, great. What if I enlarge the right-hand side by twice, right? I just scale my data twice as large. Then the space in between is become larger than the left, right? So then you will cry foul, right? That's not fair, right? Oh, then how to make it fair? Very simple, right? Normalize, right? But no, since Greeks, everybody knows, right? Why we introduce metric in the first place, guys? Normalization, right? Because you want to compare 2 things, right? Representation learned at different layers, or the representation learned by different networks. Which one is better, which one is worse? You have to normalize your currency, right? Then all you have to do is just normalize the scale, turns out. Put them on a sphere, make the total energy constant. That's it. Frobenius norm is the same, that's it. Of course, in practice, people, as I said, the same thing can manifest in different ways, right? Batch norm started with people figure out as a layer norm, instance norm, group norms, all kinds of norms. Guys, all my life, I've been doing all these things, data analysis. There's always only one purpose of normalization, for comparison, make fair comparison. Then just be clear what you are comparing, right? So then is this really, the object function makes sense? It turns out that there's some early evidences, yes, theoretical evidence shows that this exactly gives you what you want, right? This is the first sufficient condition shows that, right? Indeed, your feature achieved maximum coordinates, the rate reduction when the subspace are orthogonal, if there's enough space, highly incoherent. And not only that, the data in each subspace will become highly isotropic, nearly isotropic, meaning that it will maximize its variance within each subspaces. the higher the object function actually prefer higher, fatter, subspaces, as long as they're discriminated. So this is changing a little bit, right? The Aristotle told us that the whole is greater than sum of the parts. So here, the principle, we just change out one word, right? The whole is to be maximally greater than the sum of the parts. That's what we want. That's what we actually gain. Okay, why we spend all the trouble to learn representation? We want to gain that thing. Right? Be very, very clear what to get. Actually, people actually tried to, with similar ideas, to see, can you work with nuclear norm, right? Remember, try to encourage discriminating between different subspaces. We know that the low dimensionality can be measured as a convex term, right? Turns out that actually this is, in this case, the nuclear norm is not tight enough, right? You can play with this kind of norm. It will encourage discriminative, but not encouraging dimension. You will get a one-dimensional. You cannot avoid the neural collapse phenomenon. You can actually mathematically prove that you reach maximum 0 in this case, that when the subspace are orthogonal, actually dimension is 1 preferred, right? So this is actually something that it's kind of delicate. The log determinant is quite magical, and we'll get to know more about its property. Of course, that people say that, these days, engineers say that we actually can do, contrastive learning, contractive learning, right? Turns out that actually the rate reduction actually contrast, you can actually contrast, triplets, quadruplets. As long as if you know they're from different classes, you can do that, right? It's very, very uniform. Doesn't matter the size of the class. So anything good come out of this? Yes, and so now you can train neural networks, right? But by monitoring 3 quantities, physically, geometrically, statistically meaningful quantities, right? How the total coordinates, how the difference increase, and so on. So what's the difference? So here is a fair comparison we had with the traditional cross entropy, right? You replace everything else exactly the same. The networks, we train residual networks. The only thing we change is the object function. The data, everything is the same, exactly the same. Training algorithm, everything is the same, right? So now you can see that you get 10 classes on CFA. Each class actually have a 10-dimensional, clearly 10-dimensional subspaces, or give or take. And also what's surprising is that you can actually see the confusion matrix across different classes. Honestly, I have never seen this clean. When the first student got this, I thought they actually had some mistakes, right? So this actually really pushed all the 10 classes of the CFA to 10 orthogonal subspaces. Very, very clean. There's no confusion in between. And this is what you get from cross entropy, the angles between the features and so on. And not only that, right? Just to show you, convince you there's no neural collapsing. We actually, remember, we only have the 10 labels, right? 10 classes. I mean, each class has, about 12 some dimensions. Pack this features in all this 12 dimensions. So then we actually take, because it's a principle, we can just do a principal component analysis of each cluster and find those components, 10 components, along each component, each direction of the axis of the principal components, we find the images aligned the best with them, right? You can see that each of the, so this algorithm automatically, the objective automatically sorted data in terms of internal structures. Even we did never label this at all. Right? Each class capture statistically coherent, consistent images for you for free. During the training, it's already done. Right? And not only that, right? This is the objective function, because no longer we are not feeding the labels, right? We're using the label as side information to help us learn something about the data structure. Hence, if you have corruptions in your data, this will be very robust, right? This is compared with cross entropy, right? 10, 20, all the way to 50% of corruption, random corruption of the labels. You can see that the MCR, the rate reduction, the performance degrade very gracefully, right? Much, much more gracefully. We'll get back to this in a second, right? So also you can do in the interest of time, I'll not do that, right? So all I'm to just tell you that if you don't have labels, fine. And then every sample is its own class, right? And just have a bigger pie, right? It's augment your data and call all the augmented data as one class, you actually get the state-of-art clustering algorithm, unsupervised clustering algorithm, right? This is in the NIPS paper, right? Compared to other. There's absolutely no hack, no heuristics, right? And all the other algorithms we compared to, you should compare with their object functions, right? Or what they do in order to get the state of art. So are we happy, right? The question is, are we happy now? Yes, we actually a little bit, right? So at least we know the objective functions start to make a little bit sense, right? We're not fitting the labels. We actually learn something meaningful. We know the feature lie on the subspace is, geometrically more interpretable. And also we know they're more robust because we don't fit labels anymore, right? But there's a big but comes in, right? The network is still borrowed, right? We still borrow neural networks. It's still a black box. What happens in between, we don't know, right? Why do we need a deep networks at all, right? We are learning that about a map, right? There's nothing mathematically theoretically says why we should use layers, right? How wide, how deep? What are the roles of those linear, nonlinear operators? Why do I use convolution? Anything else? Why do we do that, right? So the question here next is, can we make this process white box? Again, the good things about from first principle, you don't care, right? You just do what you set out to do, right? Along the way, you'll pick up a few treasures. That's the point, right? So back to this is the object we want to maximize, right? Then we maximize it, right? Don't get distracted. Another practitioner report they got 5% more than the old data sets, right? Don't get distracted. This is what you set out to do, then do it, right? And then what do we do optimization? Let's just start with the simplest one, right? This is the object function as a function of z, the features. They want to maximize it. And then we just do a greedy descent, right? It's maximization. And because, again, I have to normalize a feature, and then I do projected greedy descent. This is the simplest scheme you can ever think of, right? Optimization 101. Then let's just do calculus, right? Well, then how do we do the greedy descent? To compute the gradient of the first term, the second term, right? Things start popping up, right? The first terms look like this, right? It's a matrix hitting the data. It's the second term is a matrix associated with each cluster and hitting the data with the membership, right? So put them together. The gradient of the reduction is looks like this, right? Linear operator starting z and the linear operator. And also we know the geometry, right? The first term is trying to expand, right? The second term is trying to incrementally compress each cluster, right? Because make the codiness less, right? Then what are those linear operator? You ask, right? This looks a little bit complicated, which are for everyone who's familiar with the statistics, right? You recognize in one shot, right? This is exactly the ridge regression. You're using the data as regressors to representing every data point you have. So using their labels to explain yourself. So we call it a self-expressive or auto-regressive regression, right? So this is exactly. And also one thing turns out interesting that you have a lot of points, right? You try to regress the same other points. Maybe you pick too many. Maybe there's too many noise in other data points. Maybe you are overfitting the data. Would that happen? Turns out the theory that people developed to explain that there won't be overparameterization precisely explaining this situation, right? When you have more samples, actually the bias variance will drop, right? Actually, this is also one of our recent work. When we did this work, we have no idea actually helps here, right? Because we're trying to explain neural networks, not this one. But turns out it fits here even better. So now, how do we do? This is just on the training data, right? I can optimize the moving around the configuration, maximize. How do I extrapolate it to the whole space to learn a feature map? Then all you have to do is extrapolation, guys, right? So for points beyond a lot of the training, you don't know. The only term you don't know is its membership. But since you know what the geometric quantity, the CZ is doing for every point, it's precisely computing the residual of each point to each cluster. Remember the minimal incremental codiness? This is exactly doing that. The CZ is exactly doing that. Then once you have a residual, then you just do a soft clustering, right? So assign the points to the closest cluster, right? Using a soft mask. Of course, people call this different names: gating, selection, function, whatever. It's just doing collection, right? Then suddenly you had a very simple network, right? So if you write down the algorithms, optimization algorithms for maximizing the coding rate, rate reduction, right? It's just the incremental plus this is a gradient term, right? Now the gradient term is you hit the data, the input with linear operators, and also there's the k channels. Then you do a gating in the end, soft mask, right? That's a nonlinearity. Now we even know why we need a nonlinearity, right? This is the first place nonlinearity comes in, right? Or normalization is the first place. This is the second place, right? So now you actually end up, you look at these things, right? Start to draw, we're all engineers. Let's draw a diagram of this operator. You get a neural networks, right? Input and the parallel channel, and take a comparison with ResNet or ResNext network, or mixture of experts, or RedoNet, or capture network. Take a look at the comparison, right? Of course, those networks are developed from trial and error. This tested, it worked. But this is completely, the network on the left-hand side is completely derived from scratch, right? Every parameter is computed, right? You don't, by construction, right? You don't even need to learn anything, right? It works, right? So this is some simulations, right? You can see that starting with the initial configuration, you will make the orthogonal and also compress each cluster. And that's what you wanted. There's no, I say that again, there's no backpropagation. The network is unrolling from the very beginning, from the objective, and you're done. Every parameter, convolution, and everything is computed automatically. And now, of course, that's vectors, right? You get the networks, but what about image? I do computer vision. You know, we care about the recognition, right? In computer vision, we care about the recognition. We want it to be invariant, right? The digit shows up everywhere in any angles. We want to say they're the same thing, right? So that's the sort of invariance for classification. So therefore, we want, can we do this? What happens with this rate reduction or with the recompression point of view for this? Right? Well, just write down what you want, right? As I said, this is the best methodology and it really should be the only methodology. Make it clear what you want, right? So fine, you want your, all the data, if they're shifted, they should belong to the same class. That's it, right? Don't be distracted. Don't be by another neural networks come up. Oh, I have to understand what it is doing. No, don't do that, right? It's a new species. See, guys, if the new species gets discovered tomorrow, right? We don't go back to redo the theory of evolution. You know what I mean? Right? Figure out what really the evolution is trying to do. So this is actually something that then you put those together. Those are all the data. So they all should stay together with each other, right? So every point sample, then I consider all its translated version. They should all be clustered together, mapped to the same subspace. That's it, right? Turns out something magical happens here. Oh, actually, I didn't know this. The first time I know this. So remember this linear operators, right? So we derive from the gradient ascent algorithm. They actually automatically, in this case, become convolution. You don't have to try, oh, I want invariance, I want equivariance, since I built every layer using convolution. No, you don't do that. It's the objective stipulates, if you want invariant, classify all the data, shift the data into the same class, into the same subspace, then those layers, gradient, has to be convolution as a necessary condition. Right. There's actually another fundamental, I'll be quick. So tension here. There's something people don't pay attention, right? There's actually a conflict between invariance and the separability, right? If in one class I have a delta function, say an image of the sky, right, like the stars, right? If you allow to translate everywhere and then do superposition, then you cannot, then that class alone can generate any signal in the world, right? Then what you're talking about, they're separable, right? Or you say, well, maybe the spaces is not enough. Let's lift it, right? That's everybody does in the first stage of neural network. We lift it thousands of channels, right, up. Hopefully, maybe enough space we can separate them. No, even you do that, you still cannot, right? Turns out, as long as your lifting is linear, you cannot separate the inseparable. What's the magic? What is actually the next ingredient you really need? You have to impose that you only allow your data to be generated by a sparse model. You cannot allow arbitrary number of superpositions, atoms, to add together. You only allow sparse of those gets mapped together. So this is the implicit assumption everybody assumed, but nobody spelled it out. Right? Otherwise, all the separation is meaningless. Right? So this is actually, that's actually precisely explain why we lift the data into higher dimension, then we do a sparsifying with threshold out. Make the data separable in the higher dimensional spaces. In this case, you can show precisely in this case, once you do the multi-channel lifting and do the thresholding and also consider the cyclic version, you get precisely all the E and C become multi-channel convolution. Right? So I studied neural networks for so many years. Nobody explained why do we want to do multi-channel convolution? Doing the cube thing, okay? Why not just the one channel at a time? This is the reason, right? Because this operator, E and C, has this structure. You're doing greedy descent. There's even more surprise, right? Because why? This is a humongous matrix, right? I have a lot of data, a lot of augmentation. I have to compute its covariance and also take the inverse, right? Turns out, if you consider the cyclic version, right, all cyclic matrix can be diagonalized by Fourier transform. Right? Hence, this you are not inverting an arbitrary homologous matrix. You are inverting a very structured homologous matrix. And just using, let alone there may be other structure you can utilize, right? Just the fact that those are diagonalizable by Fourier transform suggests that inverting this matrix, you can reduce the complexity. This is the number of channels. This is the number of pixels. N is the number of pixels. The cubic to something linear in the number of pixels, right? So this is the first time, right? Where you can actually mathematically prove it's more computationally more efficient to construct, learn deep networks more efficiently in spectral domain. Well, actually, surprisingly, not so surprisingly, right? There's in visual cortex, neurons actually precisely encode the transmit information in frequency, not in magnitude, right? That's why they call it spiky neurons. We'll get back to this in a second. Then for the first time, we have a white box, right? You can actually write out the whole neural networks as an optimization algorithm with every parameter spelled out, right? And in this frequency domain, everything is everything is in closed form, nothing else. And now let's put things together, right? What are the necessary ingredients in order to map a multi-class data to multiple discriminative information-rich subspaces, right? First, we need to use the assumption they're sparsely generated and lift them up so that the data becomes separable, right? And they can be close, but it has to be separable. Otherwise, the problem is not even well-defined. Second, we do rate reduction. We try to learn a better mapping, right? Push them to subspaces, make them linear, make them discriminative. That gives you, well, if you choose, guys, only if you choose. You can guess. If you're a god, you can guess, right? You don't have to. See, only if you choose to use greedy descent, you get deep networks. Okay? But if you're a god, you can just guess what the F is, right? So at least for our human beings, those are the necessary conditions, right? The sparse coding is for class separability, right? That's why we lifted channels, multiple channels, and then threshold them with ReLU. And then spectral computing, we use convolution, right? You're doing for shifting invariance. It's necessary. It's not what you want. It's not what you tested. It worked. Then you use it. No, you have to do it, right? And also deep network is for just rate reduction, greedy descent, right? So that's elephant, sort of explaining different pieces of the deep networks. Right? Actually, now you can actually do experiments, right? Remember, people have trouble with getting the neural networks to be actually really, really invariant to rotation translation, right? A lot of the neural network is actually, guys, right? Here, actually, this is just a baby test, right? We can build the neural networks again using in the convolution case, right? So guess what are the number of layers we're using? 3,500. Why do we need that? Because we want, right? Just make a point. We're not early stopping. We're not no hacking. This is just iterating. We can let this go forever. But in reality, we probably only need 20 some of them to work, right? So if you guys want the deep, go ahead. I will give you deep, right? Infinite. You can go infinitely. The network will be automatically stable. Nothing you have to worry about, right? You don't have to tune anything. You don't have to initialize anything, right? And actually, you can give very good, before training. This is after training. You can push this, the digits to very orthogonal dimensions. And there's no crosstalk. The feature across the ambiguity matrix is very clean. And again, this is a translation, right? We can think about it. We can consider this is no longer translation, a small augmentation with small translations on a few location. We translate on everywhere on the torus, right? We tested it everywhere on the torus, right? So that's why this confusion matrix is taking two samples from two different classes, rotated at every possible angles. There's no crosstalk. The same with the translation, right? So just conclude a little bit, right? So this work sort of collects, about 15 years ago about compression, right? Remember, that's the same lesson, guys, we learned 15 years ago in a hard way, right? You learn to compress, and you compress to learn, right? In the clustering case, interpolation, we minimize the coding length, average coding rate. Classification, we minimize the incremental coding length, right? Whichever give you a simplest explanation. If you want to learn representation, then measure the goodness of by the space, how big the space in between the different classes. Okay. Then if you want the neural networks, if you do this incrementally using gradient descent, you get deep neural networks. Right? And since therefore for learning, the only one objective, we want to compress, right? Because that's what we gain. We know what we gain. And also the approach. How do we do this? With our limited capability, we're not God, so we do incremental things, right? We optimize using gradient descent. We get deep networks. That's it, right? So it's very, very simple and no other mysterious. There's actually all kinds of interesting questions, right? Yeah, so theory, algorithm, and applications. Actually, my student forced me to take off some of those because they're working on some of the problems, but I'll say as much as I want. Phase transition, remember the compression, right? We know the results works very, very well, but there's no theory explaining why. And also, MCR is very robust. We saw the phenomena, undeniable, but there's no rigorous theory justifying it. Also, we did it with subspace. That's what we care, right? Or Gaussian, but what, of course, in theory, you can answer what for other distributions, right? If the Cauchy or Lagrange and so on. I mean, can you a Laplace or something, and would they give you different configuration? I don't know, right? But you can. But the theory, the framework applies, right? Also, we noticed there's a fundamental trade-off between sparsity and invariance, and to my knowledge, nobody has studied it, right? And there's tremendous things to ask. Why? When you can actually guarantee separability. And how to jointly optimize here we actually talk about most of the later parties where you're in a supervised setting, right? Where the pi is given to you, but it doesn't have to, right? Remember in the clustering case, we're precisely optimizing pi, right? Can we put those two pieces together? Right? Yes, you can, right? The number, of course, that will force you to study joint dynamics of optimizing both the representation and also clustering information. Architecture. Now, once you adopt networks, layers are actually doing optimization, right? Then all the arsenals we had, powerful tools of optimization, is at your disposal, right? Right? Can we use acceleration? If you don't like 3,500 layers, fine, make it more efficient. Acceleration, right? And there's all kinds of ideas that give you introducing additional skip networks, skip connections, right? Now you can explain everything. Well, why do you do that? Right? Separable and short. How can we make a network more efficient? Because so far we prove it's convolution. When it will become separable and short? We don't know, right? Well, that's. And also that for other groups, rotation translation works fine, but what about other groups, right? What other forms of operator will pop up? We don't know, right? By the way, everybody talk about kernels, right? So this is the work, John Ryder, we did this, even in incremental coding length paper, right? Turns out this form, the coding length is exactly compatible with kernels, right? You know, you don't have to, the covariance matrix actually can be replaced by the inner product of the two matrices, right? We know the inner product only requires the inner product. You can replace that with any kernel you want. And in fact, that's how we get much better performance. If your data has a nonlinear structure to begin with, you can use a kernel, right? But you have to guess it or learn it. So again, there's all kinds of improvements you can do. Finally, applications may be more fun, right? So how do you apply to other data? You know, I care about visual data. Maybe other people care about the dynamical data, graphical data, or group structure data, right? Permutation groups. There's some people study that, right? Better transferable. I mean, now before, see, the point is that, guys, we talk about things, transferability, robustness, without even making clear what your assumptions are, right? Very often. Now, but we know, you know, if we can learn those low-dimensional structure very well, we know how to make estimation robust to a low-dimensional structure, right? If your data lies on a straight line, if there's some outlier, we know how to get rid of it, right? But otherwise, what are you doing? Right? What you are robust against? I don't know. I don't know about you guys, but I don't know, right? So combined with, you know, also I think Roy has talked about, the previous speaker has talked about, you know, generalized models, right? Model collapsing and so on. And because we know we have neural collapse, neural networks, if you don't design in a principled way, it will collapse. It has all kinds of bad behaviors. But now I think maybe we fix one thing or two, right? How can we decompose? In fact, the idea we set out to do with the rate reduction actually has started with the conversation with Yang Kuhn. And he was actually asking, can we learn some energy or some kind of object function can help with understand decoder, autodecoder, coding, autodecoding, right? So I hope that this will give some new ideas to that directions. Finally, I want to point out that this is very incidentally, I just got to know this very recently, right? So remember that big elephant, right? Sparse coding, spectral computing, and also subspace encoding, right? Turns out those are exactly the three prominent mechanisms in the visual cortex, in the human brain, right? Sparse coding, I don't have to mention that. You know, the visual, especially in the visual neural networks, the computing spikes, they're using they're computing the spectral domain. Finally, a very recent work from Caltech, this is 2017, they actually realized they put those sparse and coding, spectral coding in the study the primate brain for face recognition. They actually discovered something quite interesting, right? Facial image in the high level features can be linearly reconstructed using response of 200 cell space. And those cells are not encoding exemplars. Unlike previously, they are encoding the coordinates. They're the axis of the subspace. Very surprisingly, they have very good evidence. So basically, sparse coding, spectral computing, subspace embedding, already explored by nature. And we know they are necessary if you want the process to be efficient, to be correct. Right. So those are some of the references related to this, learning about compression and rate reduction. Okay, as I said, you know, many of the work we didn't know at the time. We're actually already doing things beyond deep learning, the clustering, classification, and we're actually very much on the right track. And really, the recent work is just the almost immediate application of what we did about 15 years ago. And this really leads to a very constructive way of deep networks, right? What really I cannot create, I cannot understand, right? Guys, you know, I encourage you to just create things from scratch, right? Don't just take something, you know, black box and think you can use a couple of tools to disassemble it, right? That's what we did when we were kids. I think when we all grow up, we should be able to do things in a more methodological way. So, I mean, finally, I leave you part ways with you with the slogan, right? I mean, you know, sort of deep convolution networks are really just iterative optimization algorithm for compression, right? Thank you very much. That's all.
Thanks, Yi, for the wonderful talk. So our first question from Ziyu Liu. You please unmute yourself and ask a question.
Hi, Professor Ma. Thanks for your amazing presentation. I think my question is one of the opening question in your slides. Is my question is, what if we only have a partial labeled training set, or we don't have label at all? How can we estimate the big pi in the rate reduction criterion?
So see, the formulation, if you look at this, right, it's only a function of z and pi, right? Of course, in the MCR work, we actually assume pi is given to you, but this quantity is not settled on any pi. You only care about this quantity should be as large as possible. That's why when in our experiments, first the pi can be noisy. We add 50% of noise to it, error to it. This will just optimize that for the data as a whole. This is the first point. The pi doesn't have to be perfect. Second, I skipped the experiment. When you don't have the pi, you can do self-supervised learning. Just call every sample as its own pi, right? Its own group, and augmented data. Then start using this. This will give you some representation, not perfect, not the optimal, but will be good enough for you to do clustering. Okay, get the state-of-the-art clustering algorithm. Second, finally, yes, you're right. This framework is actually precisely trying to unify all settings. All you have to do is that this is just an optimization problem, only that your knowledge about pi are different. If you know all the pi's, so be it, fix it, minimize z. Or if you know part of it, then again, just use it as an initial condition, optimize pi. That's why I write this too. But this is for future, right? There's a lot of things going on, even including my groups. We're actually looking at this. But this is a great question, right? But the formulation, the maximum coding rate reduction is uniform. You don't have to even change your object function. You only change how much you know about the variables to begin with.
Thank you for your explanation. I think the point is the criterion is uniform in both supervised and unsupervised setting. But yeah, a following question is, when we update the z, the latent representation, and the pi, the attribute, like in an alternative manner, will this result be trapped in a local maximum point, or
we don't know? I mean, that's the good thing about this framework is that we reduce everything to optimization, right? We leave all the questions for people like Qing and also folks are good at optimization now. And of course, as a practitioner, we can always play. There's gazillions ways, right? So just like a GANs, right? How do we do the alternative minimization? Which one goes more iteration? Which one goes less? We don't know. You can play. But this opens up all opportunities, right? Also different starting point, how much you know about pi, right? Semi-supervised or supervised or self-supervised, right? And then how do you do? And also sometimes do you make it treat pi as a continuous variables or discrete variables, right? You can relax it between 0 and 1 as a probability. You can opt it. But then what is the landscape? I have no idea. But we're working on it, right? There's a lot of people, I'm sure a lot of people are working on it, right?
Thank you.
So, but conceptually now, you know exactly when you optimize in pi, right? You're minimizing second term. That's exactly a clustering problem. Remember, I mentioned early on, right? We don't know. Actually, John and I, we didn't know how to optimize it in a global fashion. That's why we come up with that greedy merging algorithm. It's good enough for our applications, right? But it works. Again, we don't know why it works. There's a phase transition. It's very robust. We don't know. And there's no theoretical analysis why that should happen. Why this object function is has such a magical power. We don't know, right? There's a lot of statistics analysis needs to be done here. But only because our recent work, we start to realizing we need to go back to revisit all this problem. At the time, we just developed the algorithm for our purpose for image segmentation. But now we realize how important, how fundamental some of the questions are now. Okay.
Our next question is from Neil Zhang. Please unmute yourself and ask a question. Thanks. Hi, Neil, we cannot hear you.
I cannot hear anything. Hello?
Hello?
Hello? So
maybe I can ask a question instead. So sometimes the data from the same class have several clusters intrinsically. Then how can we maintain the clustering then when seeking representations for discriminated from other classes?
Aha. So good. You saw that in the practice of MCR using even neural networks or residual networks, we did experiments with the CFA, right? You can see that the principal components within each cluster subspace will start to, sort out the subclasses, different birds with different gesture, different color, different background, and so on. So we'll do that implicitly for you, but not explicitly. So that's one thing. So maybe the representation already start to encode the richness of your data in each cluster. Okay, that said, again, remember, this object function don't care, right? See, all labels are superficial or artificial, right? So this object function says, it's fine if you give me 10 classes, but within the first class, if you have 3 subclasses, if those 3 subclasses each lies on lower dimensional, separable lower dimensional subspaces, in fact, the global optimal will be force you to actually, you need to treat the first class as 3 class subclasses. That will further maximize its quantity. Okay, subject to the precision epsilon you choose. So basically your label, so even human label, that's a good thing about this object, because it's objective, right? So your human subjective labels can be wrong or inconsistent to all the structure there is in your data, right? There's no way we can guarantee that, but this is object function can help you to discover if there's additional structure. So you need to further, just like the previous question, you need to further optimize pi. It's encoded there, right? Only that your label doesn't tell you, right? It's too gross, too high level, right? So this kind of objective is really just as long as epsilon is given to me, it will tell you what the object function is. Right. Questions?
Our next question is from Diyuan Lu. Would you please unmute yourself?
Yeah, thank you very much. So I guess my question was already answered by previous one about this labeling, and there's some overlap. Then would you recommend to use MCR square as like exploratory data analysis when you don't really know how many clusters you have in your data and you have a rough idea?
Yes, you should. I mean, if I'm a god, I try all partitions, right? I'm done, right? I find the global optimal for my data. I mean, as long as you give me a epsilon, the yard, the tolerance, I find it. But of course, that's precisely not computable, right? How do we make this discovery, explorative discovery, efficient? That's really the key. Now we know we're solving this optimization problem. Now we can focus all our energy and the smartness. That's why we wrote a proposal even with Juqin just last month, precisely about those topics, right? You can imagine that even this is a lot of even complete list things you can ask, theory and algorithms, and also some are more imminent. Particularly, yes, how to jointly optimize and pi. By the way, this object function, remember, if you know the history, is first developed not for the classification setting at all, right? We actually borrowed that. It's actually from the clustering, how to get clustering make more meaningful or computable, right? And make the object function more computable, right? To replace the kind of, maximum likelihood, EM algorithm, or those information theoretical or statistical quantity, which are very, very hard to compute or impossible to compute when you're dealing with low dimensional structure data. Hence, I think the theme of this workshop is very, very important, right? I think we talk about neural networks as a big elephant. No, that's the big elephant, right? The theoretician, sometimes we try to advocate framework that's not computable for practitioners who compute. That's the biggest elephant in my view. Okay. Yes, you can do all kinds of analysis, right? Guarantee, but they're all asymptotic or computationally intractable. Then you should ask yourself, then what the heck you're doing, right?
Yeah, this and also in this MCR is tell me if I'm wrong, that using this framework actually you also get this feature representation, this entanglement for free.
Yes. And also you get, see neural network also, you can even think about the cross entropy or the label fitting is a special case of what the MCR is trying to do, right? So one hot is just 1000, right? So basically you just try to embed the whole class, the whole airplane into that 1000. Actually you get what you want, right? You get out what you set out to do. You get one feature, right? Just like the neural collapse, it's very consistent if you think about it, right? You get what you reward, right? So, but now MCR says, no, I want to reward on how much better you can understand about the data. Even the labels become side information. Help me to discover the structure of the data. Then that completely change your view, change your attitude, right? A different metric, right? Then you can actually explain more things, what happens with the things, right?
Okay,
so
thank you.
Even the neural networks, right? Even how should you, even why you need a layered structure, because you're trying to optimize it, right? It's the simplest way to optimize such an object function, nonlinear object function, which we don't understand the landscape. Maybe, the work like the previous speaker or Chin-Chi has a lot, now our understanding about the nonlinear optimization has improved a lot in recent years. Thanks for those folks. So I really hope that the next few years is that we understand the landscape, so we can design better networks, right? As I said, we're not limited to this. We know our objective now, right? It's just a matter of how to optimize. How do we get to the endpoint, right? Neural networks, those iterations are just one way to get there. By the way, so this constructive approaches, there's still no guarantee. Everything here is just necessary, okay? There's not sufficient. We cannot guarantee you will get to. So how rich the data, right? How separable they are, how sparsely separable they are. That needs to be figured out, right? Under what condition? Or also here we didn't do any backpropagation. Of course you can fine tune, right?
Mm-hmm.
The network is not different from any other networks. Go ahead. I mean, you can also do this in the spectral domain. Actually, my student wanted to do it, but realized that we didn't make it time for the deadline of the paper because they realized they implement everything. At the time, we realized we should do things in the spectral domain, right? They realized they implement everything in PyTorch. The PyTorch doesn't support complex numbers, which is a big mistake, right? So and now TensorFlow does. So that's why the student have to take time to re-implement everything. So this is just give you a little thing, right? So don't rush to build your architecture yet, right? So we haven't figured out what's the right thing to do, right? In fact, in this construction approach, everything is a white box. We know exactly those functionality of these components. CPU has advantage. That's what we found. CPU has tremendous advantage to do this. That's why we have one brain. We don't have a distributed farm of GPUs, right? So think about that, right? Our brains developed in such as more like a CPU, not a GPU, right? Because GPU is that you don't know what to do. That's why it's a fishing trip, right? You just try to figure out, right? You burn out electricity. It's not economical. But CPU is exactly, you know what to do, right? What are the main functionalities? I even want to argue, right? For example, in the E and C channels, right? How do you do the reason we have overfitting is because we free all the parameters. We don't know what they do. But now we know what EC is doing. Even I do fine tuning using backpropagation. I should not treat them as free, right? They should be constrained to improve their own local functionality. That's another reason this constructed in the white box, you don't necessarily have overfitting. We have 3,500 layers. We have more parameters than everything. We can fit anything, okay? We don't do that. Why? All those parameters are connected. They're related to one another, right? They're not free. So fine, if you treat this network as a free parameter, you can fit anything, random label, random data. This resolved that issue, right? It's not that having more parameter, you have a more powerful, you can represent. No, it's understanding how those parameters, what the rows are, how they're connected to one another, right? That's the mystery, right? So how to do this kind of backpropagation tuning? I have no idea, right? It could be constrained, have to study the variational conditions, right? They all have constraints of their own now. They're not free parameters anymore. Right, they're not a black box. You're optimizing a white box. You're tuning a white box. How to do that? We don't even have the tools. Trust me, right? Someone has to completely rewrite the tools for doing this kind of tuning. So, right. As far as I know, neural networks, the current frameworks is very bad with constraints on the layers. It's very hard to at least not very efficient. Well, you can do, but very limited things. But now we know we need more, right? We know exactly what we need.
Thanks.
Okay, see you guys.
We have a last question. I think the time is around lunchtime. So Thomas, could you please unmute yourself and ask a question?
Hello there.
Hi.
Hi. It's a very nice talk. Thank you very much. I really appreciate your work. I just wondered, I often work with time series where we would use something like the dynamic time warping for a similarity measure or dissimilarity measure. Are you aware of any work or have you worked on how you would, at the beginning part of this, implement such a thing without a Euclidean distance, with something that's less deterministic?
You mean incorporating there's temporal structures, dynamic structure in the data?
Yeah, I mean, for example, we use dynamic time warping, for example, if you have two phenomena that's, in one time series, it happens quickly, and another one, it takes more time.
Yeah. So I see what you mean. So first of all, as I listed later, right? So I do control theory. So I obviously know that I really wanted to, I'm pretty sure one of the things that was also inspired of this work was really from this kind of path optimality and so on and so forth view of this. So next thing is, of course, obvious thing is how to incorporate this to at least the linear system, linear time series systems. I'm pretty confident because that's where we know from system ID, the input output has very good low dimensional structures, right? That actually inspired the whole work about low dimensional low rank matrix recovery and so on. So that's actually very, very promising. Obviously, that has this natural low dimensional structure to explore, but it's different, right? It's dynamical space. Yeah. Now, but your question is that said, but your question is also more about so this is stretching, scaling, right? Warping in the time. Honestly, I haven't done anything. I'm not aware, but there are people have done, but not in this framework. I'm actually curious, right? So if you allow stretching, scaling in the domain, how would that? It's different from shifting, right? Different from rotation. It's different.
To account for both of those phenomena.
So that would be good. I don't know, Chichimba. I don't know if John Wright in some of the convolution studied that. I don't know, but it's different scaling, right?
Yeah. I mean, we use it for example, for remote sensing or something like this, where you're monitoring a crop growing over time. In some parts of the world, it could happen quicker, and in some parts it could take longer, or in some parts it could start earlier in the time series than later in the time series. So of course you can't just match up with the Euclidean.
Exactly. I would say that's a very, very beautiful question. Actually, you have functions that can stretch with this group action on it. I'm pretty sure there'll be very beautiful, interesting operator comes out of it. I only care about shape, right? Despite the stretching. Honestly, I'm not sure if, there's a lot of work done, but a lot of heuristic things. I don't know if anyone has done good analysis. Maybe some of the waveless folks, but not in this context, not from the compression point of view. See, now one powerful thing here now, you only have to be clear what you try to compress, okay? Right, so so just make it clear, right? Don't hide, right? So, I'm augmenting, maybe no. That's what you want. Then just be clear. Those are things you want to put them together. Then figure out the price to do it, right? What it costs to do it. That's really the attitude now. Now, so if you care about this, then the entire family of stretched function, then that's my, then figure out, then if there are two questions comes out similar to this. How do you make one class separable from another class? One function, right, with different shape as another function with all the stretched version, right? So what do you need to do? What are the features you're talking about? Why these two as functions are separable? That's a question we actually asked, we realized with John Wright, is that we also realized that, oh, there is actually a tension between sparsity and the separability or invariance. Otherwise, the problem is not even mathematically is impossible, right? It's not well defined. You are separating, trying to separate two classes which are not separable under your assumptions. So then really that makes it crystal clear. Then with this kind of warping, what do we mean by mathematically the concept those two classes still separable or multiple classes generalized? The second thing is that then once they are separable, then to optimize this rate reduction or something, then what kind of operator comes out? Right? It could be homologous, could be no structure whatsoever, but you have the translator, right? So one thing we actually realized that this darn thing, once you clear, at least for this kind of group, translation, rotation, and so on, it's just beautiful structure because of the problem, the symmetry in the data. The operator becomes structure. Beautiful structure comes out. You don't have to try test it, right? Or impose it. It just comes naturally as a necessary condition. So it'd be wonderful to see what other interesting structure pop up in that setting once they're separable, right? So now you can ask all questions very, very clearly and rigorously now, right? Rather than always sweeping under the rug and also or approximate and also right. So you only approximate when you have to, right? You have to approximate. So that's what is good about this, this kind of more rigorous or principled approach, rather than start very beginning, let's augment some, let's train. If not enough, we augment more, test again, fine for practice, that may work for many applications, but definitely cannot provide any guarantee whatsoever, right? Even before this work, right? We are not aware of any work can guarantee, those two works, right? Full silicon with simple transformations, very, very tiny deformation. And why don't deep neural networks generalize so poorly to small image transformation, right? You can test. Those are the state-of-art algorithms or network, highly engineered. ResNet, VGG, and all those networks, ResNex, they all have the same problems, right? You don't need to you just do very, very little translation scanning. All part, right? But people, this is another big elephant, right? Nobody talks about it, or talks about it they don't care about, or right, pretend it's not an issue, right? Turns out it is a very big issue, right? If in serious applications. But there is actually a theoretical way to guarantee this. It's just a matter of figuring out the price or the right way of doing it. Right. So at least in this framework, we make the price, the reward very, very clear. Right. At least the reward very, very clear. Right.
Yeah, I completely appreciate work like this. Thank you very much.
Sure. Thanks. Thanks for your question.
Thank you for your answer.
Yeah.
Okay, thanks, Professor Ma, for this wonderful talk and energetic Q&A. So let's have a short lunch break until 1, and then we can resume where Dr. Chongyu will be the moderator for the afternoon sessions.
Okay.
Thanks so much.
Thanks, Juqing. And also sorry that Samson came up today. I cannot join. Unfortunately, I cannot join the panel. But hopefully, wish you guys have a wonderful workshop. Thanks. Bye.
Thanks.